Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in this session, I want to discuss about Model Paper 2. We have Model Paper 1 and Model Paper 2. So based on this Model Paper, we will see the questions from Lubricants. One is, the topic is Model Paper 2, questions and answers. So we will solve in this one problem. A rectangular plate of 500 by 400 mm is placed over a plane stationary surface. The two are separated by oil film of thickness is 0.25 mm. The viscosity of oil is 80 centipoise. So what he has asked, determine the force required to push the plate at a speed of 5 meters per second. The rectangular plate dimensions are given, and then thickness, oil film thickness is given, and viscosity of oil also shown. Determine the force required. How much force required to push the plate at a speed of 5 meters per second. So we can use the formula for viscous force in a Newtonian fluid. So the formula is force, the required force is equal to mu multiplied with A into V upon D. So what is mu here and what is F, we will see here. So F is the force and mu is the dynamic viscosity of the fluid, and A is the area of the plate, and V is the velocity, and D is the thickness of the oil film. Already he has given in a problem the thickness of the oil film. So here first you have to write the given data, and then here write 1 centipoise is equal to in terms of Pascal second 0.001 Pascal second. So the mu is 80 cp is given in the problem. So convert into Pascal second. Now mu is equal to 80 cp. 80 multiplied with Pascal second 0.08 Pascal second. So next we calculate the area of the plate. What is the area of the plate? Rectangular plate. So L into B. So 500 mm by 400 mm. So convert into meters. So you will get 0.2 meters square. The thickness of the oil film is given 0.25 mm. So 0.25 10 to the power minus 3 meters. That is equal to 0.0025 meter. So the velocity of the plate is, in a given problem, the velocity of the plate is 5 meters per second. So now substitute these values in the formula, that is F is equal to mu into AV by D. So here mu is 0.08 and A is 0.2 and multiply with the mu is 0.08 and area 0.2, velocity 5 divided by D in meters 0.25 into 10 to the power of 10 to the power minus 3. So you will get 320 newtons. So therefore, the force required to push the plate is at a speed at 5 meters per second, 320 newtons. So like this, you have to do this problem. So only thing you have to remember, the viscous force in a Newtonian fluid is F is equal to mu A V upon by D. Next question, what do you understand with thick film lubrication and thin film lubrication? So the mechanism of lubrications here, types of lubrications are shown here. So one is thick film or fluid film or hydrodynamic lubrication. Another one is thin film or boundary lubrication. So lubrication film between the two contact surfaces is thick enough and the two contact surfaces are separated completely by viscous oil film. At this time, the frictional force of two contact surfaces are determined by viscous resistance of lubricant, and it can be take a very small value. The coefficients of friction can be 0.001. So the thick film or fluid film or hydrodynamic lubrication, and then thin film or bonded lubrication. Two types are there. We will see one by one. So here mechanism thick film, thin film, and extreme pressure one more is there, oil with chlorinated ester. So the thick film or fluid film or hydrodynamic lubrication condition under low load high speed. So under low load and high speed, a thick fluid film of lubricant is maintained between the two solid surfaces. The thickness of fluid film is at least 1000 amperes here given. So since the fluid film separates the two solid surface, there is no direct contact between the solid surface. So this thickness of the fluid film based on the contact nature between the two solid surfaces. So this reduces the wear and tear. Is no direct contact between the solid surface. This reduces the wear and tear. The coefficient of friction in such cases is low as 0.0001 to 0.03. So thick film or fluid film lubrication. Example, consider the rotation of a shaft with respect to a stationary bearing. When a lubricant is added to the system, it occupies the annular surface between the shaft and the bearing and forms a hydrodynamic remain and prevents contact between the two solid surfaces. When the load becomes very high, the lubricant will be squeezed out. Squeezed out of the wedge and friction will occur. So whenever friction occurred, what will happen? Automatically the heat will be generated. So due to more heat, the bearing or other component will be failed. So see in this you can see thick film hydrodynamic lubricants, the bearing ring lining shown as rotating shaft in a floating lubricant, and the thick film are lubricant here. There is no metal to metal contact. So that the quotient of film thickness here you can see this is you can measure with represent with H naught. So whereas in thin film or bonded lubrication, under the conditions of high load and a slow speed, a continuous fluid film cannot be maintained between the moving surfaces. Under such conditions, the thickness of the fluid film is less than the thin film, consists of 2 or 3 molecules thick. To form a thin film, the lubricant has to be adsorbed on the metal surfaces by physical or chemical forces. In some cases, the lubricant will react chemically with the metal surface forming a thin film of metal soap which will act as a lubricant. So this thin film is known as boundary film. The coefficient of friction in such cases is around 0.05 to 0.15. The coefficient of friction in this case, in thin film case, 0.05 to 0.15. A steel film or boundary lubrication. The effectiveness of boundary lubrication depends on the oiliness of the lubricant. So, what is this oiliness? Oiliness is the ability of a lubricant to stick onto the surface. Vegetable oil and their fatty acids have more oiliness. Example: oleic acid C17H33COOH, stearic acid C17H35COOH. The polar group carbonyl of these oils reacts with the metal surface to form a continuous thin film of lubricant. The hydrocarbon chain of the fatty acid gets oriented outwards in a perpendicular direction. Next question is explain the effect of temperature and pressure on the viscosity of lubricating oil. The viscosity of the lubricating oil is significantly affected by both temperature and pressure. So detailed explanation we will see. Effect of temperature on viscosity. So decrease in viscosity with increasing temperature. As temperature increases, the viscosity of lubricating oil decreases. This is because high temperatures increase the kinetic energy of the oil molecules, causing them to move more rapidly and reducing intermolecular process, which results in lower resistance to flow. For example, lubricating oil becomes thinner and flows more easily at higher temperatures, which is why engines and machinery are designed with cooling systems to maintain optimal operating temperatures. Next, viscosity index. It is a measure of how much viscosity of oil changes with temperature. Soils with a high viscosity index exhibit less change in viscosity with temperature fluctuations compared to oils with a low viscosity index. So high viscosity oils preferable for applications where the operating temperature range is wide, ensuring consistent lubrication performance. Next one is effect of pressure on viscosity. Increase in viscosity with increasing pressure. Whereas in temperature, decrease in viscosity with increasing temperature. But here, the increase in viscosity with increasing pressure. As pressure increases, the viscosity lubricating oil increases. High pressure forces the oil molecules closer together, enhancing intermolecular interactions and thus increasing resistance to flow. This effect is particularly important in high pressure environments. So, what are the high pressure environments such as hydraulic systems, gear systems, and in the bearings of heavy machinery, where maintaining a consistent oil film is crucial for preventing wear and tear. So the Barras equation, is often used to describe the relationship between pressure and viscosity. A zeta or eta is equal to eta naught E to the power of alpha P. So where eta is the viscosity at pressure P, eta naught is the viscosity at atmospheric pressure, and alpha is a pressure viscosity coefficient specific to the oil. This exponential relationship shows that even a moderate increase in pressure can result in a significant increase in viscosity. So the practical implications are engine lubrication. So engines operate over a wide range of temperatures. Engine oils are designed to maintain adequate viscosity across these temperatures to ensure proper lubrication, reduce wear, and improve efficiency. Similarly, the multi-grade oils, those are 10 W2 40. So are formulated to have low viscosity at low temperatures for easy starting and pumping, and higher viscosity at operating temperatures to maintain a protective film. Next, hydraulic systems. In hydraulic systems, maintaining viscosity under high pressure is critical for efficient power transmission and minimizing wear. Oils used in these systems must have a high viscosity index and they are capable of maintaining performance under varying pressure conditions. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.